My name is Valentin. I'm a solution architect at GridGain Systems. For the most part, I work with our customers or sometimes potential customers, analyzing their challenges, looking into their architectures, into their applications, and understanding their performance requirements, scalability requirements, and ultimately building solutions using GridGain or Apache Ignite to overcome those performance challenges they're having. And the topic I would like to talk about today is basically one of the most popular use cases that I've seen in the last several years, and I keep seeing it, probably even more and more, is acceleration of relational databases. So what happens is that there are a lot of applications, a lot of companies that obviously use relational databases like Oracle, MySQL, Postgres, whatnot. And at some point, they start facing scalability issues and performance issues. Maybe they have new latency requirements. They want, response times to be lower. Maybe they start getting more users and more users of those applications, and more requests are coming to those databases, and they need higher throughput. So they keep scaling up, right? But scaling up is not always possible, and it's limited, first of all. At some point, it becomes either impossible or just very, very expensive. And at this point, they start looking for a horizontally scalable solution to overcome this. And at the same time, they not only want to introduce horizontal scalability into their system, into their architecture, they also want to keep their database that they have at this point, right now. Because replacing a database, you can use like MemSQL or VaultDB or maybe Cassandra. There are many distributed databases nowadays that you can use, but they all basically imply that you replace your existing relational database, like Oracle, for example, with something else. This is obviously a huge risk, especially for mission-critical applications, like in banks that process money and all that. Not all companies want to take those risks. They want to keep those relational databases for persistence, for durability, to make sure they never lose their data. And today I will talk about how we can do this with GridGain or with Apache Ignite. So first of all, just a quick overview. How many of you know what Apache Ignite is, what GridGain is? Familiar with the company product? All right, quite a few. Good. So GridGain is basically provides a memory computing platform which is based on Apache Ignite. Apache Ignite is an open source project. It's free to use. It's part of Apache Software Foundation. You can download it, use it in any way you want. This is a memory computing platform which basically provides you with different capabilities for processing data in memory as well as the actual memory storage. Right, so you can use it as an in-memory data grid. And that's something I'm going to focus throughout this presentation for the most part. You can also use it as a memory database or memory-centric database, essentially using as a system of record with the transactional persistence store that is also provided out of the box. You can use it to build streaming analytics applications for real-time analytics and real-time reporting. And we also have continuous learning framework as well, which is basically a set of machine learning algorithms that can be applied in the real time while you update the data in the cluster. So all that I just listed is provided as part of Apache Ignite. So this is basically all the core functionality that we have. What we do at GridGain is we also build several miscellaneous features on top of that, mostly to support like mission-critical deployment, mission-critical applications. These are features like data center replication, rolling upgrades to increase availability and decrease downtimes, certain security capabilities, advanced monitoring capabilities, and things like that. So again, all the core functionality is part of Apache Ignite. We provide only those miscellaneous features. And we also do like services support and things like that, of course. So you've probably seen this slide a couple of times already, but I still want to mention this because I think it's quite kind of important because it basically shows a bigger picture and about what we're trying to achieve and what our product tries to achieve. Essentially what we do today in many applications and many architectures is we have two separate data stores, one for operational workloads and another one for analytical workloads, for analytical reporting, for machine learning and things like that. And what happens is that you need to move the data from the operational store to the data warehouse, and this happens like overnight or maybe even over the weekend. There are a couple of issues here, right? So first of all, this might be quite expensive because we have two systems, we have two data storages, and we need to maintain both of them, as well as the process that happens between them, the ETL process and this feedback loop that exists from the data warehouse to the operational database. So we need to maintain all those different parts, all those different components, which means more hardware, more people, and more money. But second issue is, which is probably more important even, is that this is not real time. What companies are looking for nowadays is for those updates that happen in operational data store with high throughput. They want those updates to be reflected in the analytical reports, analytical dashboards, in machine learning algorithms, and anything that they have right away, right after they get updated in the operational data store. You can only achieve that by having everything in a single system. There is no other way. If you keep doing ETL between one system to another, it's not real time. So this is something that we want to achieve at GridGain with Apache Ignite project. Essentially, we want to create a platform that can allow you to run different type of workloads on the same data set within the same cluster. In-memory computing in general is something that can help us with that, because it's unlimited scalability, it's very high in memory performance, and this is something that we're trying to do. And coming back to our topic, essentially what it means is that when you accelerate, if we have all those capabilities in place, when you use GridGain or Ignite to accelerate your database, and like imagine you pull the data from your database to GridGain, you not only accelerate the actual operational workload that existed on that relational database, but you can also use the same cluster to run analytical workload. So basically you can solve two different problems by introducing a single item in the architecture. All right, so in terms of how Ignite stores the data, so Ignite is quite flexible in terms of how it can store the data and where it can store the data. So as I mentioned, we have this persistent layer out of the box, which is optional, can be enabled, can be disabled. And we like to distinguish this kind of 4 memory modes, as we call them. First one is obvious, it's just in memory only, so you have all the data only in memory. There is no persistence whatsoever, no disk involved. This is the option that is obviously the best one from performance standpoint, but there is no durability. Right? So if you lose the cluster, if you lose all your nodes in the cluster, there is no data. So you need to figure out a way to rehydrate from somewhere else or something like that. This is okay for some use cases, but typically you will, of course, have some kind of persistence layer. And here you actually have 2 options. First one, you can integrate with a third-party database, which can be pretty much any storage because it's kind of a pluggable integration. You can implement an interface that will tell Ignite how to interact with the database, kind of on a SPI kind of architecture. But for relational database in particular, we have this integration out of the box. So there is nothing you need to code to achieve this integration. And I will show how it works at the end of presentation. And then we have our persistent store, native persistent store, which is provided out of the box by Ignite itself. It is highly integrated with the in-memory layer. It is also distributed across the nodes. It is also scalable and all that. And it actually has multiple other advantages if you compare it with a third-party database integration. However, it obviously implies that you replace your existing, if you update your existing application, it implies that you update your existing data store, which can be a relational database or something else, with Ignite or with GridGain. And you completely rip off the one you had before. That's, as I mentioned before, not something that all companies want to do. So if you want to just accelerate your existing database or application that use the existing database without replacing completely your existing database, the second option is the one you would choose. So the way it would actually work is basically you will have a cluster of multiple nodes. Every node would typically be on a separate computer or a separate VM if it's a cloud-based environment. The data will be stored on that cluster, partitioned across those nodes, so that every node has a portion of the data. And then you will have the application that talks to this in-memory data grid layer. So essentially, what happens is that you put the in-memory data grid between the database and the application, so that application goes through the in-memory data grid, getting the performance, the in-memory performance from there, because it now fetches the data in memory instead of fetching from disk. And it also gets scalability, because it can go to different nodes to get the data, to use multiple nodes to do the processing and all that. But at the same time, you have the database underneath to provide durability. And in pretty much every in-memory data grid, you will have like a read-through, write-through semantics available, which means that if you update something in the in-memory data grid, it will also get updated in the database automatically. And other way around, if you read something, if you try to read something from the in-memory layer and it's not in memory yet, it will be fetched automatically from the database as well, in case it's possible. So that's actually how any in-memory data grid works. However, and it's actually a very good solution in terms of solving those scalability and performance issues. However, there is one serious limitation here. Most of those in-memory data grids, they only support key-value APIs. Under the hood, they are essentially distributed hash tables. And when you work with the data, you are limited to those key-value lookups, which basically is the same as being limited to primary key lookup in a database. Like imagine you have an Oracle database, you like have a set of tables there, but you can only look up by the primary key. That would be a serious limitation, right? And that's what creates a huge effort when you accelerate the application that uses a relational database. Because first of all, you need to basically rewrite the whole application. This completely new approach, completely new API, completely new data model, and you need to change everything on the application level. This is a brand new application that now uses the in-memory data grid APIs. So this is a huge effort, of course, in terms of development. And also there is a big learning curve as well, because the developers who are used to SQL database, they are not familiar with those APIs, with those approaches. So that's another challenge that we have here. So we've always wanted to overcome this in certain way at GridGain, and what we ended up with, that was like several years ago, is we actually added SQL support on top of the key value storage that we have. So Ignite is actually no different. It works in the exact same way. It is a distributed hash table under the hood. You have all the key value APIs and like compute APIs, transactions, everything that you would have in any in-memory data grid. But on top of that, we also have SQL support, so that you can run SQL queries that you are familiar with, use language that you are familiar with, and this way we try to make this transition as smooth as possible. I'm not implying that it's like a zero code change when you transition from a relational database to in-memory data grid, but at least you can use SQL, and at least you can run those arbitrary searches on top of the data that you have in memory, and you can use SQL that you're familiar with. So you will have to do some changes on the application level, but the amount of those changes is reduced by having this SQL support. From the architectural standpoint, the distributed SQL that we provide is actually fairly straightforward. This is basically just another API layer on top of the storage that we already have. So you will have those multiple nodes in the cluster. The nodes will store the data. Every node will have a small portion of the data. It is partitioned across the cluster. This way it's highly scalable. You can scale out up to terabytes or even petabytes of data sometimes on big clusters. It can be dynamically scaled as well. So you can add more nodes if you need more resources. And you can do that in the real time without any downtimes whatsoever, without interfering with the queries that are executed and things like that. And on top of those nodes, you have all different kinds of APIs that allow you to interact with the data. So you have compute, you have key value, you have transactions, and SQL would be just one of those APIs. And you can mix and match them in different ways. So you can use SQL for something and then use compute for some other part of the application, for example. And you can also create indexes as well, which is also very important because most of the data grids, they provide some searching APIs, but essentially they would go through all the data, basically. Since you are limited to those key value lookups, you need to either know the primary key for the data that you need to look up, or you need to go through all the data, basically, and filter it out. This is not very efficient. This is not scalable at all. So Ignite support indexes on you can create an index on any field in the tables that you have. You can have group indexes as well that have multiple fields in them and things like that. And then use them in queries, of course. In terms of connectivity, you have several options as well. So first of all, there are native APIs. Java, .NET, and C++ have full APIs available. So in those languages, you can basically just create an application, start a client node, and then have all the APIs that we have with the product, including SQL. So you can run SQL queries from there. We also have a JDBC and ODBC drivers out of the box. So if you have a Java application that uses JDBC, you can also transition it using the fact that we provide the JDBC driver out of the box. The same with ODBC if you have a non-Java platform. We also have seen use cases where this was used for like integration with systems like Tableau and other analytical systems as well. And we also have REST API. So essentially there will be like a Jetty server embedded in every Ignite node, and those Jetty servers would expose certain REST APIs that you can use to access the data, and that also has SQL support in there. Data definition language is also supported. So this is basically just a way to define and modify schemas that you have in Ignite. So you can create or remove tables, or you can modify them by adding or removing columns, for example. So if you add something in the database, in your relational database that is underneath, you can do this in Ignite as well, right? And you can do this in runtime, again, without stopping anything, stopping any nodes or interfering with the queries. The same with indexes. You can create new indexes or drop indexes if you have like new queries that require some other fields to be indexed that were not indexed before. You can use this DDL, those DDL statements as well. And what is good about it is that you basically use standard SQL way of doing those things. There is no special API for this or anything like that. Same happens with data manipulation language, which is ANSI 99 compliant. So you have all those different capabilities. You can select by different conditions. You have joins. You have group bys, order bys, aggregations, subqueries, and pretty much anything that is available in SQL. It's all fault tolerant and consistent, meaning that if you have topology changes happening in the background while you execute the queries, the result will still be consistent, and you will never get an incorrect result for any query that you execute. And and of course, in sort, update, delete statements are also available, so you can update the data using SQL as well. You don't have to. If you want to use key value APIs for that, you are free to do that. As I said, you can mix and match those different APIs together in any way you want. But you can do this with SQL as well, from different tools, from using JDBC driver or whatnot. All right, and finally, I wanted to mention joins. Joins are obviously very important in SQL. This is kind of one of the cornerstones of SQL. And joins, and you will probably have joins in most of your queries if you use SQL to access your data. But joins have actually pretty serious complication in a distributed world. The problem is that data is partitioned randomly and independently for different tables by default. Like, as an example, let's take this simple data model where we have a city table and we have a country table. And there is a one-to-many relationship between them. We will have like a country ID field in the city table, right? And what can happen is that you will have some Canadian cities, Toronto and Calgary, on one node, and other Canadian cities like Montreal and Ottawa, for example, on other node. And the row that represents Canada in the country table will be also on the first node. So if we execute a query that joins those two tables together on every node independently, we will actually lose Montreal and Ottawa, because on the second node, there is nothing to join them with, right? So what will happen in this case, actually, if you run this in Ignite, is that Ignite will figure this out and will reshuffle the data while the query is executed. So you will actually get the correct result, but from performance standpoint, it's not going to be very good. You will probably, instead of accelerating your application, you will slow it down, which is not what you're looking for. We do support that because for certain use cases where, like, for example, you have one query out of 100 for which you could not collocate properly for some reason, but you don't really care about performance of that particular query, right? And other 99 queries, they're lightning fast. Everything is great with that. In this case, this might be okay. This is typical more for like analytical use cases maybe. But if you want to achieve the best performance from this kind of a memory computing platform, distributed platforms, you need to collocate. When I say collocate, I basically mean that you make sure that, and Ignite has a very straightforward way of configuring this. You basically just need to make sure that all the cities for the same country are located on the same node, and that's the node where the actual country is as well, right? So if we have all the Canadian cities and Canada on first node, and all the Indian cities and Indian second node, for example, then we can just broadcast this query across all those nodes and execute independently on each of them. So this removes this data reshuffling and removes the data movement between the nodes that happened in the previous case, right? So this means that you need to make some changes in the data model in advance, and you need to consider this in advance before you actually load the data into the cluster. But that would provide you much better performance if you compare that to non-collocated joins. So yeah, just basically if you accelerate any SQL-based application, always think about this. So if you just blindly load the data without doing this, as I said, you will probably slow down it instead of accelerating. Just always consider this, make sure everything is collocated, make sure that all of your joins, or at least most of them, are collocated this way so that there is no data movement and no data reshuffling while you execute them. All right, I also wanted to show how this actually works. Because it's actually fairly straightforward. When you want to import a database, import a schema from your database and apply it to Ignite and then start running queries, this is actually fairly straightforward. And let me show it to you. All right. Can you see that okay? All right, perfect. So this is actually, I have like a Postgres database running here. And it can be any database. I just use Postgres because I happen to have it in my laptop. And I have this world database in Postgres. This is like, this traditional example database with city, country, and some other couple of other tables, that is used that is used by many database vendors to demonstrate different kind of things. So we have we have city table, we have country table, and country language table. Like in city table, we have name, population, and things like that. So it's already there, right? So what I will do is I will go to the web console, which is basically our monitoring and management tool, which is provided as part of GridGain and as part of Apache Ignite. Some of the features are available in Ignite, some of them are only in GridGain. This is the full version. And the first screen that we have here is what we call a configuration screen. It basically allows you to configure any cluster, just UI to create those configurations. But what it also has here is this import from database button, where I just provided Postgres JDBC driver. I provide the URL, username, password, and it actually imports all the tables. I will import tables from the public schema, and these are those 3 tables that I just showed, right? So it imports all the definitions, all the tables, all the columns and data types and whatever we have there. And it will basically create all the data models, all the configurations, and all the boilerplate stuff that you would have to create manually without this tool. So it created this cluster. If we just go to that cluster, first of all, this is, as I said, this is a configuration screen, so you can change any different type of configuration, like I want to switch to static IP discovery here, for example. And any configuration that is available is actually here. And then I click Save and Download. And what it does, it downloads a small project that you can use as a start. It's just a Maven-based project. So it has it has POM XML and all the sources. So let me open it in. Hope it's not too small. All right. So it has basically a bunch of stuff here. I will have to change the URL of my. Can you see that fine, or is it too small? Yeah. Okay. Oh, hold on. That's the wrong one. This one. Here we go. Better? Right, so here I will just change the URL to whatever I had there. World DB, my username, password is empty. All right, so first of all, it has all the configurations ready. So this XML is like a configuration for Ignite node. So it contains all the mappings between the database and the our in-memory data model, and it's actually pretty long. So it's like several hundreds of lines of XML just to configure those 3 tables. So it's a pretty big boilerplate that you don't want to create manually, and that's what this tool allows you to do. And also there are some classes that you can use, as a start for your actual application project, right? So first of all, there are data models. So if you want to use key value APIs, you can use those objects as well, right? So even if you manipulate with the data using SQL, you can still look up a country object, actual Java object, in your code from the cluster. So you can combine SQL and key value APIs. Then there is the server node code startup, which basically just I'll use this one, which just starts a node with this XML that I've just shown. So let me start a node. It will just create a single server node, which we'll use to load the data and run some queries. Okay, so this is started, and then there is the load caches class, which starts a client, connects to that server that I just created, and loads all three caches from the database. So all that is generated. I haven't written a single line of code so far, right? So I just imported the schema from the database. I generated this. The tool generated this project for me. I just used one class to start a node, the server node, and another one to load the data. So now if we go back to the web console, and I will go to the SQL screen, and I have this notebook already prepared for this. So like first of all, yeah, we can check that we have some data. So if we execute like select count from country, for example, we get like 239. That's what we actually have in the database. And then we can execute any kind of queries, right? So we can execute a query like this, for example, a very simple one. We get like 5 most populated cities, right? So we order by population, we do limit 5, and we get name and population of that city. And that's what we get. So this is, like typical SQL query execution. You can do this from JDBC driver. You can use it from any tool. You can use it from, application that uses Ignite client to connect to the cluster, or you can use this web console tool, which does pretty much the same. It connects to the GridGain. It does not fetch any data from the database, right? So it all does, everything that we do now happens in memory. You can do more complicated queries with joins and aggregations. So here we join city and country table, and we get average city population for those 3 countries that we specify here, right? So same result. So we get the result set that we expect from this kind of query. And finally, I wanted to demonstrate the the write-through capability. So, for example, let's check what is the population of Belgium, right? This is like 10 million plus, and I can execute this exact query in Postgres, by the way. Right? I get the same exact result. So now what I will do is I will update it with some other value. Like let's imagine that population increased up to 15 million, and we want to update this in our database, right? I will do the exact regular update statement, which will be executed in GridGain, right? And because of write-through capability, it will actually be reflected in the database as well. So let's execute it. It says me that everything was okay, it was updated. So if I execute the select again, I will get a new value, right? Which is what we expect. And if I go to Postgres and execute the exact same query, it will again give me the correct result, the one that I updated with, right? So whatever update we execute on GridGain, it gets reflected in the database automatically. So you don't need to synchronize it manually. And again, whatever I did here so far, I haven't written any line of code. I haven't written any line of configuration. Nothing. I just connected the web console tool to the database, and it generated all this stuff for me. And I was able to execute fairly complex queries without doing any additional steps. All right. So what's with the time? All right. Yeah, I actually think we can move to questions if you have any.
In your example, if you update your database, table, let's say population,
Yep.
will it reflect to the GridGain cache, or is it, or you need to do a configuration for it?
Yeah, so typically when you put the memory data grid in front of a database, it's assumed that you will use the data grid APIs to update the data and to do anything, right? Obviously, it's not always possible. There are different solutions for that. So if you update the database directly, which often happens when you have like multiple applications and you transition like one by one, you don't want to transition all of them at once. There are different solutions for that. Something is needed in between to propagate those updates. So this is not something we can do on our side. There is like Oracle Golden Gate, which we have integration with in Enterprise Edition, by the way. And there are other open source. Yeah, you can use Kafka. You can use different kind of stuff. With Kafka, we also have integrations, by the way. So if you have, if your updates are propagated to Kafka from the database, then you can easily connect, consume from Kafka, from Ignite, and stream the data there as well.
Let's say you already migrated the application and you want to start using the cache API, right, instead of the SQL.
Yep.
So then let's say you're using cache APIs, you're doing a lot of gets and things like this. You do something behind in order to optimize the queries that you're doing over the database to basically insert updates, because it's not okay to do a lot of round trips to the database. So basically, how are you updating the database? Are you preserving the performance when you're moving data from Ignite to the SQL?
So I mean, yeah, if we're talking about updates on the database level, so first of all, there are two different ways of doing this. You can do this fully synchronously. In this case, whatever, updates in Ignite will be as slow as your database, right? So whenever you update something in Ignite, it will just synchronously wait for the database to be updated. There is also right behind option, which you can use for asynchronous updates. In this case, it will basically like accumulate all those updates that happen in Ignite and then flush them in batches and things like that. And it's all, this is all configurable. You can configure batch size, different timeouts, and different kind of stuff.
Two questions. The first one is, what kind of protocol do you use for transactions, given the data set is distributed?
Mm-hmm.
And the second one is, for collocating data, is that feasible through the SQL operations, or is there a separate API?
HQL, like for
SQL for collocating data for the collocated joins you mentioned.
Yeah, okay. So first one, what was the first one? Sorry.
For transactions.
Yeah, for transactions. So we have MVCC implemented, and we use two-phase commit, basically, in the general case. There are certain optimizations there, like if transaction spawns only a single node, for example. Again, if you use collocation and then your transactions actually go only to one node, then we will optimize it and use like a single back and forth message, things like that. But general case, it's two-phase commit. So for collocated, non-collocated joins, so it's still SQL. It doesn't really matter, right?
But when you write data, how do you make sure they are collocated?
Oh, okay. Yeah, it's actually defined when you create a table. So in case of, I think I had an example here. Hold on. So you can do this through configuration in this XML as well, or if you use data definition language, for example. So you see here we have, we actually have it here. So this with statement, with close that we have at the end, this is like a custom syntax that we added to a regular create table. And the affinity key there at the end is basically what defines how the data is collocated. So everything with the same affinity key will be on the same node. In this case, this is the country code field. If you do this with XML, there would be just a different way. I don't have an example with me, but you can do the same.
When you use the import of data into the grid, does it just use the primary key as your key so that you can do the get? You can sort of use the get API.
Yeah, that's the default behavior of the tool. But again, I mean, you can go like there. So if we go back to this configuration screen, right? Actually, we need to go to advanced. And then we can go to SQL schema, and then we can also, change a lot of things here. So you can actually modify it. You don't necessarily have to rely on how this tool generated it, right? If you want to make some changes, you can also do this here. You can change some data types maybe, you can change some mappings, customize different kinds.
Then you would lose kind of the compatibility with
No,
the underlying
this needs to be done with care, of course.
Okay.
I'm just saying that you can change anything here. Basically, the XML and all this code is generated based on whatever we have here. Sometimes you don't have primary key; you have to define it. There are cases when you actually have to do those changes.
About the data affinity, it seems like quite a black art. Say if you've got city code and then you want to add another thing that isn't city code, but they might have both those attributes, then you've got to really kind of balance and consider where you want the best performance. Are there lots of tools to help you do that? Or is it really truly just black art?
Yeah, I mean, there is no single answer here. I mean, the data modeling in a distributed system might be quite challenging. And sometimes you need to do a lot of things in advance, right? And yeah, I mean, adding new tables and applying like new collocation to data model that you already have might be difficult. But again, I mean, I wouldn't say that I've seen the cases where, where data model had to be changed like completely from what it used to be before. So, yeah, I mean, I guess there's no easy single answer here, to be honest, right? I don't know if that answers the question, but.
I was hoping that you say there are some tools that we use, query planning, to work out where the effort is spent getting data.
No, yeah. I mean, of course, when you created a certain version of data model, right, and then you can analyze how queries are executed. So you can look at the execution plan. Like if I go back to the SQL screen, like just as an example, where is this one? So I have like explain button here, and it actually shows me like an execution plan of how query is executed, right? So there are different ways of analyze how query is actually executed. And here in this particular case, like we have a scan of the city table, for example, because I actually don't have any indexes yet. I didn't create it here, and data set is very small. But that basically would most likely mean that you need to do something on the indexing level, right? If you don't have collocation, if there is data reshuffling, you will also see it here and things like that.
Is there some automated way of keeping schema?
Yeah, you can also use the same ways like Oracle Golden Gate and others. Like Golden Gate for sure propagates schema changes as well to the caching layer. I'm not sure about those open source solutions. I would doubt actually. But Golden Gate, since it's like, because the schema change always primarily happens on the database side, right? So you will first change the database, and then you need to propagate it to the in-memory layer. So you do this either manually or through things like Golden Gate. Because, in-memory layer will never know about anything that happens on the database side. Database has to push it back to the in-memory layer.
I see it's a multi-connected clusters. Does that mean you can have it sitting over two databases? So I was thinking of a scenario where you've got globally distributed data with a China database and a UK database, for example.
Yeah, that's actually but use case I've seen multiple times. Especially like, in banks, I know a couple of banks that created basically like an enterprise level cache that would accumulate data from different data sources. And they're not even necessarily two databases. That can be two different things. Like they have Cassandra for some data, mainframe for something else, databases, Hadoop, whatnot. And they kind of accumulate this data from different data sources into a single cluster and then do some processing there. So.
Are there some key gotchas with doing that sort of thing?
Not really. The only thing is that, you will probably not achieve full consistency, especially if you do like transactions across this data or something. This is more for analytical workloads, right? When you just basically pull all the data into memory and then you do some processing based on that.
Can we create a composite key?
Yeah. Yes. Absolutely.
Can you just show any one of the example how we define this activity key? Then we create this composite key. Then how we define it as an activity key? We give a separate entity name or something like that.
So yeah, it depends on how you create the tables and how you configure them. There are basically three major ways to do that. There is an annotation-based way, so you can have, just an object like, in this case, you will have a city key object, right, with a city ID and a country ID. And then you will just mark this country ID field with a special annotation, right? You can also do the same in XML. So in XML, you just specify that you have a cache key, which has two fields, and then one of them is affinity key. So you just provide the name there. Or as I showed before, with DDL, you just provide it as a part of this with clause there. So it would all depend on how how you configure that. But as a matter of fact, with affinity key, if you do collocation, the actual cache key for the table that you collocate this way will always be a composite key, because you will need to have like your actual primary ID and the ID that you use for affinity for collocation.
So there's two questions I have. One is the vertical data type support, like blob to blob, that support. Or second question is the NoSQL database support part of the memory? We know the MongoDB now is and the persistence layer can do it, but what about memory NoSQL support?
Yeah, I mean, you can just. We actually have integration with Cassandra if we talk about NoSQL databases.
No, that's the persistence layer I'm talking about. In memory, like your SQL server, like RDBMS, memory, everything memory, right?
Yeah.
You're playing the memory. Same thing, the NoSQL playing the memory.
Yeah, I mean, you don't have to use SQL. Again, I mean, there are all those different APIs are available. You can mix and match them in any way, and you don't have to use SQL. I worked with multiple customers who only used key value APIs. Sometimes that's what they want, especially for like distributed caching, there's things like that, right? Or
what are the blob and glob?
Yeah, I mean, I think blobs are supported for sure. I do not remember about clubs specifically, but I would just, if you go to the documentation, there is just a whole list of data types. Hold on. Yeah. So this is the actual page. So if you go to the Apache Ignite-SQL.readme.io, that's the documentation for SQL, and one of the pages there is the list of.
The question I asked because Oracle blob support 120 terabyte one field, so the size matters.
It does. Yeah, that would be. I mean, you don't have to move all the data into memory, right? So that would be probably something that I would look at before just moving this data as is into memory. All right, we're running out of time. I will be actually at the GridGain booth for the next hour or so. So if you have any more questions, you can find me there. All right, thanks so much.